Okay, this question here is a problem with a graph. Okay, you're given the mesh that is suspended vertically from a fixed point with a spring there. Then different meshes are suspended from the spring, and then the length of the spring and the weight that you added, they are plotted on the graph here. Okay, and the straight line graph is drawn. Now, look carefully at this graph here. The normal graph, we often have F against L or something like that. Okay, but this graph here is actually L on this side and F on the other side. Okay, so in the normal kind of FL graph, if you want to find out the work done, is area under the graph here. So if for this kind of graph, when you draw it this way, where the L against F, is the area should be counted on this side here instead. Okay, so be very careful with this. So let's look at this problem here now. Okay, we'll come to this issue later on. Let's look at this first part of the question. Is quite straightforward. First part says that the weight of 4 Newton is suspended, is then pulled further by 0.8. So what is the total length of the spring? So this weight here is 4 Newton. So the weight 4 Newton, then all you need to do is look at this point here and then go up and read the intercept where it cuts the line, and which is here. Then you read off from here is about 9.2, right? 9.2 cm. So when the 4 Newton is hung there, it's already 9.2. So you pull down with another 0.8. So 9.2 plus 0.8. You add another. You pull down with your hand to stretch it down by zero point 0.8 meters. So 0.8 cm. So you become 10 cm. Okay. So the total length is actually 10 cm. So this is actually a very simple 10.0 cm. Okay, to be consistent. Right, so it's a very straightforward data reading from the graph. Next, you are asked to find the change in the gravitational potential energy of the mass. So this is simply change in GPE is simply mg times the change in height. Change in height, you change it by 0.8. So it's mg is 4 Newton, so it's 4, and the change in height is 0, 0.8 times 10 to the power minus 2. Okay. Okay, so next, a change in gravitational potential energy. Then what about the uh, change in elastic potential energy of the spring? Now, as I mentioned earlier, we start from here, then we stretch until here, the end. So when you calculate the area, it's not this area. Normally, when you plot FT graph, it's area here, but now we're not. We're not plotting FT graph, but rather we are plotting distance against force. Force is on the horizontal now. So it should be this area instead, okay? From 8, from 9.2, from here until towards the end. So from here to here, this area, okay? This area here, area of that trapezium here, okay? It's stretched from here to there. So you have to work out the area of that trapezium, and that should be quite easy to work out. So this area of trapezium, so that will be half the length of both sides here. So that is 4 plus 5 times 8.8 cm. Okay, the increase. Okay, you look at the area. This is this length is 4. Okay, this length is 4. From here to there is 4 Newton. The top portion is 5. Okay, so is area trapezium is the sum of two sides divided by 2, then times the increase in height is 0.8. Okay, so you work out this, and that will give you the, again, in elastic potential energy. Okay, All right. The last part, use the answers in part 2 to show that the work done across additional extension is 4 times 10 to the power minus 3. Now, over here, when you work out the gain potential energy, the change in gravitational potential energy, you get 3.2 times 10 to the power minus 2. So as you can see from here, the answers in part 1 and part 2 are not the same. There's a gain. Part 1 tells you the loss in gravitational potential energy. Uh, they drop by a certain height, and part 2 says there's a gain in elastic potential energy, and this is 3.2 times 10 to the power minus 2, and this is 3.6. They are not exactly the same magnitude. So you actually gain more elastic potential energy than the gravitational potential energy that is lost from the 4 Newton weight. So that accounts for the work done. That means your hand have to do this work. So the difference in these two is 3.6 minus 3.2 times 10 power minus 2 represents the work done by the hand, okay, by external force to pull down. Okay, so the answer is therefore 0.4 times 10 to the power minus 2. So that is 0.4 times 10 to the power minus 2 joule. Okay, so that's the end of this part here.